So 400 million years ago, swimming around the ocean were fish that had vestibular organs like our own, the inner ear, the part of the ear that senses motion and gravity. That's 200 million years before the dinosaurs were on the planet. And if you look at the fossil record, the semicircular canals that sense angular motion and the linear motion sensors look much like the ones we have today in humans, in modern humans. And it kind of speaks to how important this sense really is. So a lot of the work in our lab is centered around hearing and balance, and what can we do to understand better how hair cells function, how the inner ear functions, and what can we do to treat disorders of the inner ear. So my previous student, Sarud Rajguru, came to the lab and we started recording responses of neurons to pulsed laser light, and I was just astounded that they respond amazingly in phase lock. So for every laser pulse we got an action potential. And the potential of this for making cochlear implants and other therapeutics is really profound. Resolution. So cochlear implants, although they do restore hearing and give some people, deaf people, the ability to understand speech, they're not good enough to allow you to appreciate music or to really control the timing of sound going to the ear. So we have a lot of hope about using pulse laser light to make a cochlear implant, vestibular implant for restoring hearing to the deaf, for example, restoring balance to those that don't have it. And the same kinds of technologies, I have another student working on using it for deep brain stimulation for movement disorders, for example, Parkinson's or other types of movement disorders. The Brain Institute has served a little bit like a meeting point and nexus, bringing people together. Along with the Youth Star program, we've been able to recruit some really top-notch people recently. And I'm really excited about that, and I'm delighted about the opportunity of being able to work with some of these people and learn new things.